Swayam Prabha. Digital India. Educated India.
So, today we will continue our lecture on analyzing trusses. In the previous lecture, we saw how to analyze the trusses and determine the forces that occur in the members by the method of joints. The method of joints is conveniently used to determine all the forces in all the constituent members of a truss. But in certain cases, we may be interested in finding only the forces in certain members or a single member. In such a case, the method of joints is not an efficient method, and we use another method called as the method of sections, and today we will see how to analyze trusses by method of sections. As the name suggests, this method involves creating sections and the free body diagrams of the sections to determine the various forces in the truss. Let us consider an example. Here you see a truss A, B, D, G, C, E connected at G by a pin joint and at E by a roller joint, and on some external forces P1, P2, P3 acting on the truss. If, say, we are interested to find the forces in the member BD, BE and CE alone, then it is not very efficient to find these forces by method of joints, because in order to determine this force in BD, first we have to move from either joint G or E, where only two forces are unknown, and we have to move one joint to another joint. So, the method of section uses a portion of the truss and the free body diagram of the portion of the truss to determine the internal forces. So, here let us consider this section NN, which passes through the members BD, BE and CE, for which we are interested to find the forces. Then we can consider the equilibrium of either the section ABC or the section DEG to determine these forces. But if we use the free body diagram of this portion, that is DEG, then one has to determine the forces, the reactive forces at G and the reactive forces at E. But if we consider the free body diagram of this portion ABC, then we do not need to determine either the reactions at E or G. So, let us use the portion ABC to analyze this truss. This is the free body diagram of the portion ABC. Since the section passes through the member BD, BE and FC, we have to include the forces set up in these members in the free body diagram. We assume that all forces are tensile in nature, so the forces are acting away from the joint. That means the force FBD and the force FBE are acting away from B, and the force FCE is acting away from the joint C. The equilibrium of this portion is maintained if the sum of all the forces is 0 and the sum of the moments of this force about the point is also 0. So, we have 3 equations from this free body diagram, and the 3 equations can be used to determine the 3 unknowns. Since we have only 3 unknown forces in this free body diagram, this problem is a statically determinate problem and we can solve it. Here we can note that the forces FBE and the force FCE are concurrent at E because the member BE and CE are connected at this joint at E. So, it is convenient or judicious to use the moment summation about this point E in order to find this force FBD, because the moments of the force FBE and FCE will be 0 about this point E. In the same way, the members BD and BE are concurrent at B. So, the moments of this force FBD and FBE are 0 about this point B, and if we take a moment summation about this point, it is possible to find this force FCE. And the third equation could be a force summation, either the summation of the vertical components or the summation of horizontal components can be equated to 0 in order to determine the force FBE. Let us see an illustrated example to see how we use this method of section for determining the internal forces in a truss. Here we have considered the same example that we used for illustrating the method of joints. You see a truss ABCD supported at A by a pin joint and at D by a roller joint, and some external forces, say 10 kilonewton force at F and 5 kilonewton force at E. Let us say we are interested in determining the force in this member BC and the force in this member FC and the force in this member FE. We see that it is possible to create a section passing through the member BC, FC and FE such that the section passes through only 3 members. So, if we consider the portion of the truss ABF, then we will have only 3 unknown member forces if we have determined the pin reactions from the free body diagram of the entire truss. In this problem, we can also consider this section because it is also possible to determine this reaction dy. So, we can consider either the portion containing ABF or the portion containing CDE. So, in order to proceed, first let us find the reactions, that is at A and D, from the free body diagram of the complete truss. Here you see the free body diagram of the complete truss. We have replaced the pin connection at A by the two reaction components AX and AY, and the roller has been replaced by a vertical component of the reaction force. And the problem is statically determinate, and from the three equations we can determine the three unknowns, that is AX, AY and DY. Now let us consider this section ABF to determine the forces in the members BC, FC and FE. So this is the section that we are going to consider. Let us create the free body diagram of this section. Since this section passes through BC, FC and FE, the forces in these members have to be included in the free body diagram of the portion of the truss. Let us assume that all the members are subjected to a tensile force because of the loading. Thus, these forces act away from the corresponding joints. That is, the force FBC acts away from the joint B, and the force FC and the force FE acts away from the joint F. Here we see that the members BC and FC are concurrent at C, and so it is judicious to use a moment summation equation about point C to determine the force Fe. Same way we see that the forces in the member FC and the force in the member Fe are concurrent at F. So, it is judicious to use a moment summation about this point F to determine the force FBC. And the third equation could be a force summation equation to determine the force in FC. So, we have first the moment summation about the point F. So, when we compute the moment of the various forces about this point F, we first have the reactive force at A, which is 8.75, and the moment of this force about this point is a clockwise moment, so which is a negative sense, and the moment arm is 2 meters. So, we have 8.75 times 2, which is a negative moment, and the moment of this force FBC is also a clockwise moment, and so negative. So, we have minus FBC, and the moment arm is 4 meters. So, we have minus FBC times 4. From this equation we have the force in BC determined as minus 4.375 kilonewton. Since the answer has turned out to be negative, our original assumption that the member is in tension is wrong, and actually the member is in compression. So, the force in the member BC is 4.375 kilonewtons of compressive nature. In the same way, we take the moment summation about this point C. We have 4 times of force in Fe, because the momentum of this force is 4 meters, and this is a counterclockwise moment and thereby a positive moment, plus 10 times of 4, the moment of this force 10 kilonewton, again a positive moment because it is counterclockwise about C, and the moment of this force 8.75 kilonewton reactive force is a clockwise moment about C, and thereby it is a negative moment, and this equation gives the value for the force in the member Fe as 3.125 kilonewton. The third equation, we can take either a force summation about x axis or a force summation about y axis. Here we have taken the force summation about y axis and we have equated to 0. From geometry we get the direction cosine of this force Fc as since we are summing up the vertical components, we need to know the sine of this angle, which is 4 by 5.657 times of force in Fc plus the vertical reactive force, which is positive in direction, and the applied force is negative because it is a downward force, so minus 10. From this equation we have this force in Fc as 1.77 kilonewtons. So, this problem illustrates how we can use the method of section to determine the forces in the members. Few things you would have noted, that we create a section such that the section only passes through 3 members. Since we know from the equilibrium equations of a rigid body in plane, we can only determine 3 unknowns. So, it is judicious to pass a section passing through only 3 members, because the internal forces in the members are unknown, and if we pass the section through more number of sections as more number of members, then it is not possible to determine those forces by only considering the free body diagram of the section. So, let us see few problems, a simpler problem first and then a little more complex problem to see how to use this method of section to solve the problem on truss analysis. Let us consider this truss ABJK, which is a simple truss, planar simple truss, connected by a roller at this joint B and by a pin connection at joint K, and certain applied loads, say 4 kilonewton at D and 4 kilonewton at G. The various dimensions and geometry of the truss is given. Let us say we are interested in determining the forces in the members AD, CD and CE only. From the geometry of the truss, we can see that it is possible to create a section that passes through, let us consider this section AA, that passes through the member AD, CD and CE. Since the section passes through only 3 members, if we consider the free body diagram of this portion containing A, B, C, then it is possible to determine the forces in the member AD, CD and CE. But before we can proceed to do that, we have to determine the reactive force at B. So, first consider the free body diagram of the entire truss to determine the reactive force at B. So, let us consider the free body diagram of the complete truss. We replace the roller at B by a vertical reaction By. We have an applied force of 9 kilonewtons at A, and we have the 4 kilonewton forces applied at D and G. The pin connection at K is replaced by 2 components of reaction Kx and Ky. the various dimensions are needed to compute the moments, like this is 15 meters and this is again 15 meters and so forth. So, if we consider this free body diagram, and since we are going to use this section ACB to determine the forces, we are interested in determining this reaction By. So, from this free body diagram we can see that if we take a moment about this point K, then only By is the unknown force and it can be determined. So, let us write the equation taking the moments about K and equating it to 0. Since the force at B is an upward force and the moment of this reaction is clockwise about this point K, it is a negative moment. By times the moment arm is 15 plus 15 plus 15, that is 45 meters. The moment of this 9 kilonewton force is a counterclockwise moment about this point K with a moment arm of 8 meters. So, since this moment is a counterclockwise moment, it is a positive moment. So, we have plus 9 into 8. The moments of this 4 kilonewton forces at D and G are also counterclockwise about K and thus they are positive moments. So, we add them 4 into the moment arm of this is 30 meters plus the moment arm for this 4 kilonewton force is 15 meters and we equate this to be 0. Because for equilibrium to exist, the moment of all the forces about a point has to be 0. From this equation, it is possible to determine By and it has been found to be 5.6 kilonewton. Since now we have determined this reaction force at B, we can consider the free body diagram of the section AA, the portion of the truss ABC to one side of this section AA. So, let us draw now the free body diagram of the portion of the truss containing ABC. Since the section passes through the member AD, we have to include the force in the member AD and it also passes through the member CD. So, the force in that member has to be also included. We assume all these forces to be tensile forces. So, the forces will be acting away from the corresponding joints. That means, the force AD will be acting away from A, force CD will be acting away from C, force CE will be acting away from C. We also see from geometry that these two forces are concurrent at D and these two forces, that is FCE and FCD, are concurrent at C and the force FCE and FAD are concurrent at A. From this free body diagram, we can now write the equilibrium equation to determine these three unknowns. We need also certain dimensions in order to find the moment arms. So, this is 8 meters and this distance is 15 meters and this is half of that, which is 7.5. So, the slope of this line is 7.5 and 4. So, let us write the equilibrium equations from this free body diagram. And since we have seen that the forces are concurrent, like the forces FAD and FCD are concurrent at D, and these two forces are concurrent at C, and these two forces are concurrent at A, it is convenient to consider the moment equations. So, the first equation that we write is the summation of the moments about A. For your convenience, we have considered this section AA. If we take the moment summation about A, since these two forces are concurrent at A, we have only this force in the member CD, which is unknown, and all other forces, that is the reactive force at B, the applied force of 9 kilonewton at A, are all concurrent at A. Thereby, the force in the member CD has to be 0, because the moment of this force cannot be balanced by any of these forces. So, from this equation we find that the force in the member CD is to be 0. Now, let us consider the summation of the moment about C, where the force in the member CD and the force in the member CE are concurrent. So, this can be used conveniently to determine the force in this member AD. So, we have the 9 kilonewton force and the force in AD. So, 9 minus the force in AD is the resultant force at A, and the moment arm of these forces about C is half of this distance, that is 8 meter, which is 4. Then we have this force, that is the reactive force By, and the moment arm of this force with respect to the point C is half of this distance, that is 7.5 meters. So, it is minus By times 7.5. We see that this force By has a clockwise moment and this force has a counterclockwise moment. So, this is a positive quantity and this is a negative quantity, and we equate this to 0. Since we have already determined this force By, now from this equation we can determine the force in the member AD, and it has been determined to be minus 1.5 kilonewtons. Since the answer has turned out to be negative, our original assumption that the force in the member AD is tensile in nature is not valid and the force is compressive in nature. So, that means the force is 1.5 kilonewton compressive force. Now, let us consider the moment about D, because the forces FAD and FCD are concurrent about D, it is possible to determine the force in the member CE from this equation. So, the equation is the moment of this reactive force By is minus By times 15, and since this is a clockwise moment about D, it is a negative quantity. The moment of this force 9 kilonewton force about D is 0, the moment of these two forces is also 0. The moment of this force FCE is not 0. The force FCE can be resolved into two components, and the horizontal component of this force is going to have a moment about d, and the vertical component of this force is not going to have a moment. So, in order to determine this, we need to know this angle theta and the cos of this angle, and we already know the slope of these lines, and from that we know that cos of theta is equal to 7.5 times by root of 8 square plus 7.5 square. So, the horizontal component of this force is going to have a counterclockwise moment. So, it is a positive quantity FCE cos theta, and the moment arm is 8 meters into 8 is 0, and from this equation we determine FCE as 11.9 kilonewton, and since this is a positive force, it is a tensile force. So, this problem illustrates how we can use this method of section to determine the forces. Let us now consider another class of trusses that we call the compound trusses. A compound truss is a rigid truss constructed by connecting two or more simple trusses. We have already seen how to construct simple trusses. A simple truss, let us say ABC, is shown here, which can be constructed by taking a triangular truss and connecting two members and a joint. And in the same way, this complete truss ABC has been constructed. So, this green truss what you see is a simple truss. In the same way, we see another truss D, E and F, which is again a simple truss. Now, these two simple trusses have been connected by the links BD, BE and CE to form a rigid truss, and this complete truss formed by connecting the two simple trusses is known as the compound truss, and it has been supported by a pin at A and a roller at F. There is another configuration by which also it is possible to connect the two simple trusses. Here you see another compound truss. The two simple trusses are A, B, C and B, D and E, and here they have been connected by a pin at B and a member CD, and this combination also results in a rigid connection of the two simple trusses. Let us see some conditions that have to be satisfied for the compound truss to be also statically determinate as well as rigid. We have already seen that simple trusses are rigid as well as statically determinate. Now, let us derive some conditions that are necessary for the compound truss to be statically determinate as well as rigid. So, we see that this kind of trusses cannot be created by the triangle algorithm that can be used for creating simple trusses. The triangular algorithm is that for a simple truss we connect two members and a joint in order to build this simple truss. The same algorithm cannot be used to create this compound truss. And we see that even if we remove one of these members, let us say in this compound truss the member BD or the member BE or the member CE, the rigidity of this compound truss is lost, and either this portion DEF starts to rotate with respect to this simple truss ABC. So, this 3 connection, that is BD and BE and CE, are optimal connections to ensure rigidity. Here we see that these 3 links BD, BE and CE are non-concurrent. That means the 3 links does not pass through a single point. Instead of having this connection, let us say CE, if we had a link connecting B to this joint, then this complete truss can rotate about this point B. Or if we had, instead of these 3 connections, if we had a link connecting these 2 members, then also this portion of the truss can rotate, because all these 3 links BD, this link as well as CE are of equal lengths, and this complete truss can rotate with respect to this simple truss ABC. So, this condition that the 3 links should be non-concurrent as well as they should not be non-parallel should be satisfied for the connection between 2 simple trusses to be rigid. If 2 simple trusses are connected in a rigid way, then they have similar properties of static determinacy and rigidity as for the simple trusses. That is, the equation that m plus 3, if m is the number of members and r the number of external reactions to be determined and n the number of joints, then the equation m plus r equal to 2n, which was satisfied for the simple trusses, is also satisfied for a compound truss. Let us see this example. Here we have 2 simple trusses ABC and DEF connected by 3 links BD, BE and CE. Let us count the number of members. We see that the truss ABC has 13 members and 8 joints. So, this is the number of members and this is the number of joints for this simple truss, and same way we have 13 members for this simple truss and 8 joints for this simple truss. Additionally, we have 3 members connecting the 2 simple trusses and the joints are not increased. Okay. So, the total number of members in this case is 26 plus the 3 connecting links, that is 29, and the total number of joints is 16. So, if we see in this equation, the number of members is 29 plus the external reaction, here we have a pin connection, so 2 unknowns, and here we have a roller connection, so 1 unknown, so R is 3. So, we have m plus r is 29 plus 3, which is 32, which is equal to 2 times of n, where n is the number of joints, which is 16, and it is equal to 32. So, this equation we see that is satisfied for this compound truss. So, let us see how to analyze such compound trusses by, say, method of sections. If we are interested to determine all the forces in the members, then we may use the method of joints, but if we are interested to determine only certain forces in the compound truss, then we can use the method of section. So, here you see a roof truss which is known as a Fink roof truss. You see that it is a compound truss constituting of two simple trusses, one AHE and the other HKO, connected by a pin at H and a member EK. So, and we are interested in finding the forces in the members DF, DG and EG. In order to determine these forces, we can conveniently use the method of sections. So, in order to use the method of section, we have to see if we can pass a section which passes through the members of interest, that is DF, DG and EG. Let us consider this section AA. If we consider this portion of the truss, we see that we have four unknowns, that is the force in the member DF, the force in the member DG, the force in the member EG and the force in the member EK. We know that in 2 dimension, from the equilibrium equation of rigid body, it is not possible to determine more than 3 unknowns. So, now we have to see how we can determine one of the unknowns. Say the force in this member EK has to be determined. In order to determine this, we can consider another section, say BB, which passes through HJ and this member and this member EK. Now, we see that since this section passes through only 3 members, it is possible to determine all the 3 forces. So, once we have determined this force EK, now we can go back to the previous section and now only we will have 3 unknowns, that is DF, DG and EG, and the problem is solvable. So, let us try. Before solving this, we have to determine the reactions at A, which can be done by considering the free body diagram of the complete truss. Let us draw the free body diagram of the complete truss. Here I am only showing the salient features. We have 2 components of reaction, AX and AY. At A, since at A the truss is connected by a pin joint, and at O, since we have a roller, we have a single component of reaction OY. Other forces are acting at various points. Since the entire loading is symmetrical, I am just drawing one half of the truss. All the forces are in kilonewton. Some dimensions are required to compute the moment arm. All these individual distances are 1.45 meters. Let us use this free body diagram to compute the reaction at A. If we use this equation sigma fx equal to 0, this results in Ax to be 0, because all the applied loads are vertical in nature and we do not have a horizontal load. So, the horizontal reaction also vanishes. So, Ax is 0. Now, by using this equation sigma Fy equal to 0 and the symmetry that exists, we see that this reaction Ay has to be half the total load that is acting on the truss. We determine Ay to be 9005 newtons upward in this case. Now that we have determined the reaction, we can use the free body diagram of the portion of the truss constructed by this section BB to determine the force in this member EK. So, let us draw the free body diagram of the portion of the truss constructed by using the section BB. So, here we are interested in constructing the free body diagram of this section BB. Here we have this force Ay which has been determined. So, let me draw this diagram for clarity. And since this section passes through the member Hj, we have the force in the member Hj and we have the force in the member Hi as well as the force in the member Ek. All the forces have been assumed to be of tensile in nature. And we know this reaction Ay which has been determined as 9005 Newton, and various applied loads are also known. 1.13, all forces are in kilonewtons, 2.25, 2.25 and 2.25 kilonewton. The horizontal separation between all these forces is 1.45 meters from the geometry of the truss. So, let us write the equilibrium equations from this free body diagram. Since we are interested in determining the force in the member Ek, it is convenient to take the moments about this point H, where the force Hj and Hi are concurrent, and the only unknown will be the force in the member Ek, and it can be determined. So, let us write the moment summation about H and equate it to 0. So, this results in the moment of the 2250 Newton forces are: the first moment of the force is the counterclockwise moment of the force at this joint F, which is 2250 times this distance, that is 1.45 meters, and this is a counterclockwise moment. So, it is positive, plus the moment of the applied force at D, which is again 2250 into 2 into 1.45, which is the moment arm. Again this moment is a counterclockwise moment, plus the moment of the force at joint B, which is again 2250, and the moment arm is 3 into 1.45 meters, and the moment arm of this force is 1130 times 4 into 1.45, again counterclockwise. The moment of the reactive force at A is a clockwise moment, so it is negative. The force is 9005 Newton as determined times 1.45. Into 4. So, this has to be equated to 0. From this equation, and also we have the moment of this force in Ek, which is a positive moment Fek, and the moment arm is 2.9 meters. So, sum of all these moments is equal to 0, and from this equation the force in the member Ek can be determined, and it is determined as 9000 Newton, and since it is positive, it is tensile in nature. So, from this free body diagram we have determined the force in the member Ek. Now, it is possible to move to the free body diagram of the portion which is sectioned by the section surface AA, that is, it passes through the member DF, DG, EG and EK. So, let us draw the free body diagram of this section. We are assuming all forces to be tensile in nature. So, they act away from the corresponding joints. We have the force in DG and we have the force in EG and the force in Ek. The reactive force Ay has been already determined. This is a known quantity, this is a known quantity, this is a known quantity, and so we only have 3 unknowns to be determined. We see that these two forces, that is the force in the member DG and the force in the member EG, are concurrent at G. So, it is convenient to take moment about G to determine the force in DF. Same way, we see that these two forces, that is the force in DF and the force in DG, are concurrent at D. So, a moment about this point can be used to determine this force in EG. So, let us start by considering first the moment about D to be 0. Since these two forces FDF and FDG are concurrent at D, their moments are 0, and only we have the moments of this force FEG, the moment of this force FEK and the moment of this force AY in the moment summation equation. So, that is equal to 1.5 times 2250, because we have some applied loads at these points, the 1.13 kilonewton force, the 2.25 kilonewton force at B, A and D, So, when we take the moment of all these forces about this point D, the moment of this force is 0, the moment of this force which is 2.25 kilonewton force about D is 2250 times 1.5 meters, which is the moment arm, 1.45 sorry 1.45 meters about this point D, and which is a counterclockwise moment, and so it is a positive quantity, plus 2 into 1.45 times of 1130, because that is the moment arm of this force, minus, because the moment of this force Ay is clockwise, and so it is a negative quantity, 2 into 1.45, which is the moment arm, times the reactive force, which is 9005 newtons, and the moment of this force Fek is a counterclockwise moment. So, it is a positive quantity, plus 1.5 times the direction cosine of this force Eg, plus 3.6 minus 2 into 1.5 times the force in the member, Eg. So, this results in finding the force in Eg as 4.56 kilonewton, and since this is a positive quantity, it is a tensile force. Now, we can use the force summation equation to determine the other two forces. So, first we use the force summation about y axis. The various direction cosines are available. This is for the member Eg. The direction cosine is 4 by 5 times the force in this member, minus 1 by root 5 for the force in Df for this member. This is the direction cosine, plus all these vertical forces, that is the reaction force at Ay, which is 9005 kilonewtons, then all the applied forces which are downward. We have 1130 Newton at A, we have 2250 Newton at B, and another 2250 at D. So, the sum of all the vertical components has to be 0, and this results in the force in Df as 105,709 Newton, and since this is a positive quantity, again it is a tensile force. Now, we can use the force summation about x to be 0, the positive axis is the positive x axis. We have this 9000 Newton force in the member Ek, plus the component of the force in the member Eg, plus the component of the force in the member Df, plus the force in the member DG, which is a horizontal member, and so the force in the DG has to be added. So, from this equation we have this force in DG is determined as 2312.9 Newton of tensile nature. So, we have seen how to analyze the method, how to use the method of sections to solve compound trusses. So, any problem on trusses, either it is a simple truss or a compound truss, can be solved for determining the internal forces if the problem is statically determinate by the method of joints or the method of sections. And method of section is conveniently used if we are interested in determining all the forces, and the method of section is used if we are interested in only in certain of the members. In the method of sections, the key to the solving is to find suitable sections such that at a time only 3 forces are unknown. If more number of forces are unknown, then we may use additional sections to determine the unknowns and then solve the problem. With this, we complete our discussion on analysis of trusses, and we will move to analyze other kinds of civil structures like beams in the next lecture.